Hello everyone, this is Karthikesh Srivastav. I am a candidate master on code forces, 5-star on CodeChef, ICPC Kanpur Mathura Regionals 2020 rank 27 and global rank 251 in Google Kickstart Round Day 2021. And today I am going to explain the problem Farmers of Wasseypur from code Senso. The difficulty level of the problem is easy and the prerequisites are DP on trees. Now let's move on to the problem statement. So, given a tree of n vertices and n-1 edges, each vertex of the tree has exactly one value which is either 1, -1, 2 or -2. The product of the path between two vertices u and v is defined as the product of the value of vertices lying on the path. Among all such pairs u and v, we have to determine the maximum product path and return it modulo 1 e power 9 plus 7. Okay, so if we are considering a path from vertex u to vertex v, and suppose that this is vertex z, this is vertex x and this is vertex y, okay, then the product of the path from u to v would be equal to a of u into a of v into a of x into a of y and this multiplied by a of z. Okay, so this would be the product of the path from u to v. If you cannot see it at that time, then you can see it now. It is a of u, a of v, a of x, a of y and a of z. All the vertices which are lying on this path from u to v will be the product of the path. Okay, so among all such pairs u and v, we have to determine the maximum product and return that maximum product modulo 1 e power 9 plus 7. That is our task. We can easily solve this question in order of n square by iterating over all the pair of vertices, but that is not the logic here. We will solve it using DP on trees. So here are some assumptions for the DP solution. Okay, DPU0 denotes the number of 2's and -2's on the path with positive product, maximum magnitude, or basically the path which is having a positive product and the maximum magnitude, positive product and the largest in magnitude, that is starting from the node u and ending at any node v which lies in the subtree of u. Okay, and in the same way DPU1 denotes the number of 2's and -2's on the path with negative product and maximum magnitude, that is starting from node u and ending at any node v in the subtree of u. Okay, and let me explain you with an example. Suppose that this is node u, okay, and here is its subtree. Then the path that we are talking about, it can start from this node and at this node. It can start from u and at 1 and at 2 and at 3 and at 4, 5, 6, 7 or 8. Okay, so we are basically talking about a simple path that starts from a node and ends at any other vertex in its subtree. Okay, we are not talking about a path like this such that it starts from 5, goes till u, then goes back till 7. We are not talking about any other path. We are only talking about simple paths starting from u going till 4, starting from u going till 5, starting from u going till 1, starting from u going till 2, starting from u going till 3, starting from u going till 6, starting from u going till 7 and starting from u and going till 8. Okay, so among all such paths that lie in the subtree of u, dp of u0 stores the number of 2's and -2's on the path which is having the maximum positive product, and dp of u and 1 stores the number of 2's and -2's on the path which is having the negative product with the maximum magnitude. Okay, so let's see the calculation of dp of u0 and dp of u1 with these two examples. I have written two examples here. Okay, now for this example, let's first calculate it for the node number 11. For node number 11, what would be dp of 11, 0? What is 11, 0? A path which is starting at 11, going at any subtree in 11 and having a positive magnitude. Okay, 11 is the only node in its subtree, so there exists no such path. But yes, when we are talking about positive magnitude, then we can consider that, okay, we will not take this 11 and keep it as empty, and if it is considered empty, then the magnitude would be considered 1. Okay, So what would be the number of 2's or minus 2's in it? It would be 0. So you can see that dp of 11, 0. Here it is 11. dp of 11, 0 is 0. Okay. Now it is having a value of minus 1. So what would be dp of 11, 1? What would be dp of 11, 1? The negative path is having a magnitude of minus 1. What is the number of 2's or minus 2's? The power of 2 or the power of minus 2. What is it? It is 0. So it would also be 0. Okay. We are only dealing in powers of 2's and minus 2's. Okay. Now come on 10. Here is the node number 10. So what is the maximum positive product path that starts from 10 and ends at any node in its subtree? It starts at 10, ends at 10. What is the value? The value is 1. So what would be dp of 10, 0? The number of powers of 2 or minus 2's in 1. It would be 0. You can see that it is 0. Okay. Here. Now the negative path which starts at 10 and ends at 10. There is no such path. So and an empty path cannot be considered as negative. So we will fill it as minus 1. Minus 1 indicates that there does not exist any such path. Okay. You can see it here. Now let's come on the vertex number 9. So 9 is having a value of minus 2. Okay. Now we have to determine a path which starts from 9, ends at any vertex in its subtree, and is having a negative magnitude and a positive magnitude, and both in terms of the maximum magnitude. Okay. So if 9 is having a value of minus 2, so it is having two childs, 10 and 11. Okay. And 9 is having a negative magnitude of minus 2. So the power of 2 or minus 2 is already 1. Now since 9 is negative, so if it would take 10's positive value, then negative into positive would be negative. Okay. And if it would take 11's positive value, then it would also be negative. So what is the maximum power of 2 that it can get? So it is 1 plus 0, which is obviously 0, and 1 plus 0, which is 1 plus 0, which is 1, and 1 plus 0, which is 1. So here I would write it as 1. You can see that this path, okay, start from here and go till here. Start from 9 and go up to 10. So this path has a magnitude of minus 2, and the power of 2 or minus 2 in this path is basically 1. It is minus 2 raised to the power 1. Okay. So here I have written 1. Now what is the positive product? You start from 9 and go till 11. Okay. So this path has a product of minus 2 into minus 1, which is equal to 2, and it can be written as 2 power 1. So the power of 2 is 1. So I can write it as 1. Here I have written 1. Okay. dp of 9, 0. Now let's come on the node number 8. So here is my node number 8. So 8 is having a value of 2. So starting from 8 and ending at 8, what is the value of the path? It is 2. What is the power of 2? It would be 1. A positive path which is having a power of 2 equal to 1. Now since 8 has the value of 2, so there does not exist a path which is having a negative value. Okay. So I would fill it at minus 1. Minus 1 represents that there does not exist any such path which is having a negative value. Okay. And all these are powers of 2's and minus 2's. Okay. Now let's come on to 4. Okay. So here is at 4. 4 is also similar to that of 8. 8 was having a value of 2 and 4 is also having a value of 2. So it would be similar to that of 8. 8 was having 1 and minus 1. In the same way 4 would be having 1 and minus 1. Okay. Now let's come on to 7. Now here is 7. 7 is having a single child which is 9. Okay. Now 7 is having a positive value which is of 2. If I include 7 in the path, then it would definitely have a single power of 2 because it is itself having a value of 2 and it is positive. Now if I want positivity for 7, then I will take positive value from its child. And who is its child? 9. What positive value 9 can afford? It can afford of 1 and power of 1, a power 1 of 2, and 7 is also offering a power 1. So 1 plus 1 would be 2 here. And what negative power 9 can offer? It can offer of 1, and 7 is also offering of 1. So 1 plus 1 is 2 here. Okay. And I can show you here. You can see the path that starts from 7, go to 9 and 11. So this path is having a product of 4, which is equal to 2 square, and it is a positive path with maximum magnitude, and that starts from 7, goes to 9 and then goes to 10. This is having a product of minus 4, which is equal to minus 2 square. So in this in this particular thing, the number of minus 2's, or basically the number of 2, the powers of 2 in the absolute of this negative value is 2. Okay, so I can write here that, okay, the powers of 2 is basically 2 in the absolute value. So now let's move on to 6. Now you can see 6 is having a negative value. Okay, so if I combine 6 value with 8's positive value, it would result in a negative value. And if I combine the value of 6 with 8's negative value, then it would result in a positive value, because negative and negative is positive. So let's move on to 6. Here is 6. Okay, 6 child is 8. Here is 8. Now you want positive value for 6. What value is 6 offering? It is offering minus 2. So it is already negative. You want a positive value. So take the negative of 8. Is 8 offering any negative? No, 8 is unable to offer any negative. Okay, so 6 cannot offer any negative. 6 cannot offer any positive, because it is itself negative and its only child cannot offer any negative. So a negative into a negative is a positive, but it is not possible here. But we can consider an empty path. So an empty path has a value of 1 and the power of 2 in it is 0. Now let's consider a path, a negative path. Okay, so what is the value of 6? It is minus 2. So it is negative. So in order to have a negative value, its only child 8 should offer 6 a positive product. Okay, so what is it offering? It is offering 1, which is 2 power 1. So 2 power 1 into minus 2 is minus 4. And what are the powers of 2 in it? 2. So basically I will write here 2. Now let's move on to some other nodes, which is as 3, 2 and 1. Okay, so let's move on to 3. Okay, so the only child of 3 is 6 and 3 is having a value of minus 1. Okay, so in order to obtain the positive value for 3, I will look at the negative value of 6. It is 2 and 3 is having a magnitude of minus 1. So a magnitude of 1. So it would be just copied here. Simply it would be copied here. And in order to get a negative value for 3, I would look at the positive value of 6. It is 0. So it would also be 0 because it is 1, magnitude of 1. So it cannot offer anything. Okay. Now let's look on to 2. So when we are talking about 2, 2 is having two childs, 4 and 5, and it itself is having a positive magnitude of 1, or it itself is a positive value. 2 is having two childs, which is basically 4 and 5. Okay, so when considering the positive value for 2, so 2 is having two child, which is 1. 4 is offering a power of 1 in positive. Okay, 5 is offering a power of 3, which is offering better, 5. Copy it here. Now 4 is offering nothing in negative, 5 is offering 3 in negative. Copy it here. So this is done. Okay, now let's move on to 3. I have done of 3. Now let's move on to 1. Okay, so 1 is having a magnitude of 2 and a positive value of 2. So it is already offering a single power of 1. So what are the childs of 1? The childs of 1 are 2 and 3. Okay, so 2 and 3. Now the positive value that 2 has to offer is 3 and the positive value that 3 has to offer is 2. So I would prefer this value. It would be 3 and 1 plus 3 is 4. Now the negative value that 2 has to offer is 3 and the negative value that 3 has to offer is 0. So I would prefer this value and it would be 1 plus 3, 4. Okay, so basically in this way we compute the DP values for the whole tree. Okay, now let's look at a second example. Now in this example as well, for the node number 11, let's start from the node number 11. So does it has to offer any negative value? It doesn't has to offer any negative value because it is a positive node and it is a leaf. So it cannot offer a negative value. So just fill it with minus 1. Can it offer a positive value? Yes. What magnitude? 2. What is the power of 2 in it? 1. Just fill it. Now come on 10. Now can it offer negative value? No, it cannot offer negative value. Fill it with minus 1. Can it offer a positive value? Yes, it can offer a positive value. What magnitude? 1. What's the power of 2 in it? 0. Just fill it. Now just come on 9. What is it? It is minus 2. Can it offer a positive value? Yes, but it would be empty. So what would be the power of 2? It would be 0. So it would be 0. Yes, come on 9. Can it offer a negative value? Yes, for sure it can offer a negative value. What is the value of the negative? Minus 2. What is the power of 2? 1. Fill 1 here. You see 1 is filled here. Come on 8. 8 is having 2. Can it offer a positive value? Yes, for sure. What is it? It is 2. What is the power of 2 in that? It is 1. Can it offer a negative value? No, 8 cannot offer a negative value. So fill it with minus 1. Come on 7. Can 7 offer a negative value? Yes. What it is? It is minus 1. What is the power of 2 in absolute of minus 1? It is 0. Just fill 0. Can 7 offer a positive value? No, but it can offer an empty path. So what is the value of an empty path? 0. Empty path 1. So what is the power of 2 in an empty path? 1. It would be 0. Okay. Now just come on 2. Now 2 is having 3 childs, 7, 8 and 9, and itself having a positive value. Okay, 7, 8 and 9 itself having a positive value of 1. In order to construct the positive value of 2, I will just take the maximum of the positive values of 7, 8 and 9, which is 1 of that 8. Now 1 plus 1 would be equivalent to 2. You can see it from here. Now in order to construct the negative value of 2, I would take the negative values of 7, 8 and 9, which is 0, minus 1 and 1. 8 cannot offer a negative value, 9 can offer and 7 can offer. So what is offering the best? 9. So 1 plus 1 will be 2 here again. So these are the negative offerings. Okay. Now let's move ahead. So we are on the node number. We have computed for this node. We have computed for this node. We have computed for 10. We have computed for 11. So now we have to compute for the node number 6. So what are the two childs of 6? 2 and 10. Okay, let's come on to 6. Two childs of 6, 2 and 10. Here is 2, here is 10. What is the value of 6? It's minus 1. So in order to obtain a positive value for 6, 6 will look at the negative value of 2 and the negative value of 10. 10 has nothing negative to offer. It is minus 1. 2 has a negative to offer. It's 2. So 2 will be copied here because 6 has a magnitude of value of minus 1 and a magnitude of 1. So it has 0 powers of 2 to offer. So it would be just added here. And when talking about the negative value of the path starting at 6, it is here. You have to consider the positive paths that is starting from its child. It is here. It is having 2 powers of 2. From 10 it is having 0 powers of 2. 2 is offering a better path. Just add it here. It would be 2. So you are also done with 6. Okay. Now let's come on to 5. So when you are at 5, you know that what would be the positive and negative offerings of 4 and 3. So come at 5. Okay. Now you are at 5. What value 5 is having? 5 is having 2. So it has a power of 2 to offer and it is positive. So in order to construct its positive value, you will look at its children's positive value. It has 1 to offer, it has 0 to offer. Take this one. 1 plus 1 is 2. Now, in order to construct its negative value, you will look at its children's negative value. 3 has nothing to offer, 4 has 1 to offer. Just take this one. 1 plus 1 would be 2. Okay. So this 5 is also constructed. Now you are on the construction of 1 which has 3 childs, 5, 6 and 11 and has a negative value. So in order to construct the negative value of 1, you have to look at 5, 6 and 11. Negative value of 1, 5, 6 and 11 positive values. It is offering 2. 6 is offering 2. 11 is offering 1. Who is offering the best? 5 and 6. It is 2. Just copy 2 here because 1 has no power of 2 to offer. It has 0. Okay. Now, in order to get a positive value of 2, positive value at node 1, you will look at its child's negative values. Since negative into negative is positive, the negative values of its childs. 5 is offering 2. 6 is offering 2. 11 is not able to offer anything. It is here. So the maximum is 2. You will just copy that 2 over here and it is here copied. Okay. So basically this is the construction of this table, and I just wanted to that you all should know that what is this dp of u0 and dp of u1. This is a really important thing that you should understand in order to solve this problem. Okay, now it's all simple and cakewalk from here. Now see, there can be multiple cases. This is the first case. This is the vertex v. It is having two childs x and y, and this is a dummy child z. Okay, now for this dummy child, the negative value, it cannot offer any negative value, but it can definitely offer an empty path. And I told you that in an empty path, what is the magnitude of the empty path considered? It is considered equal to 1. What is the power of 2 in this empty path? 0. So just write 0. And this particular empty path has a positive value. And what are the number of 2's and minus 2's in its magnitude? It is basically 0. And does it has any negative part to offer? No. So just write minus 1 here. Okay, so this is basically a dummy child. Now, how can you obtain a positive product path that is passing from the vertex V? by using the DP values of its children. How can you obtain that path? Let's see. V is having a positive value. You take the positive value of x, multiply it with the positive value of y, and multiply it with the positive value of v. Positive into positive into positive, it's greater than 0. Now, or you take the negative value of x, multiply it with the negative value of y, multiply it with the positive value of v. It would also be greater than 0 because negative into negative cancels out, becomes positive, and this positive is greater than 0. So this is the first case. When a of v is greater than 0, then in this manner you can obtain a path that is passing through vertex v having a positive magnitude and the number of 2's or minus 2's. Basically the power of 2 in that path would be dpx0. The path you considered from the child x is having a positive magnitude. The path you considered from child y is having a positive magnitude dpy0, and a of v is equal to, then just add another power of 2. Now the path you considered from the child x is having a negative magnitude. The path you considered from child y is having a negative value. Sorry for using the word magnitude. Okay, it's having a negative value. The magnitude is always positive, and the vertex v is positive because it is assumed here. So this negative into positive is greater than 0, and that's why, because we are always ending up at positive, so we would want this particular magnitude to be maximum, because we have to maximize our answer, and if the magnitude is maximum, then it is in our favor. So that's why we computed the maximum magnitudes, and that's why we computed the magnitudes in powers of 2, because the power of 2 in this question can go up to 1 e power 5. There might be a path which is having 1 0 0 and this much numbers of 2 in it, and if you try storing 2 raised to the power this in an integer, it would definitely overflow. And that's why I'm storing the magnitude of a path in terms of the number of 2's or minus 2's that particular path has. Because if a path is having 100 2's in it, and if a path is having 200 2's in it, then this particular path is definitely having a greater magnitude than the path having 100 2's in it. Okay, now there is another case. If a of v is negative, then there is also a case of dummy child, which has a positive part to offer, which is of magnitude 1, and the powers of 2 in it is 0, and it doesn't have a negative part to offer. So if it is less than 0, then how can you construct a path of positive product passing through the vertex v? How? See, from node number x you take a path of positive, from child y you take a negative path, and from here you take a negative path. Okay, the value of node v is negative. From x you take a negative path, from y you take a positive path, and from v you are taking negative. So here negative negative cancels out, it becomes positive. Here negative negative cancels out, it becomes positive. So this is also greater than 0, and this is also greater than 0. So this is how we basically, it is always greater than 0. See, we only want the maximum magnitude. So the maximum magnitude, why we were trying to store the maximum magnitude, is satisfied. Okay, and we only want the powers of 2's or minus 2's. So we can determine that what is the possible magnitude. Okay, so the number of powers of 2 in a positive part, that is starting at the child x, the numbers of powers of 2 in a negative part, that is starting at a child y, and if I am a minus 2, if the v is a minus 2. Now the number of powers of 2 in a negative part, that is starting at a child x. Now the number of powers of 2 in a positive part, that is starting at child y, and a of v is equal minus 2, then another power of 2 is added. So that is another case. Now here there are two ways that a path passing through node v can be constructed in two ways. For example, it starts from a real child x, goes to v, and then doesn't go anywhere. Basically it traces a dummy child, and a dummy child is nothing. Basically it is an empty path. So it can be a one real and one dummy child, or it can be like this. It can start from x, go to v, and then go to another child of v, which is y. Both children are real, or there can even be a third case. This is z1 is a dummy child, z2 is a dummy child. It starts from z2, which is an empty path, goes to v, then goes to z2, which is also an empty path. So it consists of only the node v. So what does this path comprise of? X to v. What does the second path comprise of? X to V to Y. And what does this comprise of? Only V. Okay, now let's discuss a few more things. Okay, now here I am just storing path of 0. What does path of 0 mean? It is written in the DP assumptions. Let's read that. See, path of 0 stores the maximum value of DPU0. What is DPU0? It is the number of 2's or minus 2's in the positive product maximum magnitude path, which is starting from node U and ending at any node in the subtree of U. So basically, path 0 stores the maximum value of DPU0 of all the children U of node V encountered till now, and path 1 stores the maximum value of DPU1 of all the children U of node V encountered till now. Okay, because we only need the maximum magnitude, as I have shown you here. The magnitude, basically the size turns out to be positive, so we need the maximum magnitude. Okay, now let's move ahead. So if a of v is greater than 0, okay, now what does path of 0 store? Path of 0 stores the maximum magnitude of what? dp of all the child 0 values. Okay, and path 1 stores the dp of all the child 1 values. So basically path 1 is storing a negative path, path 0 is storing a positive path. Now if a of v is greater than 0, then you take a positive path from x. If I am to then just add one more power of 2 and take a positive path from all the nodes which has been processed before x. Suppose x is processed at the last, y has been processed, w has been processed, u has been processed. Okay, and path of 0 stores the maximum of dp y naught, dp w naught, and dp z naught, because, or basically dp u naught, because it is always optimal to process that only, because it is always optimal to take the maximal value. Okay, now we can also do it in this way. We take the negative valued path in the subtree of x, starting from x, going in the subtree of x, a negative value path, and a negative value path among all the remaining nodes that has been processed before x, which is the dummy child z and u, w, and z, anything. Okay, and I just, this is negative, this is negative, this is positive, this negative cancels out, it becomes positive, and this is a positive, so this is also greater than 0. Now if a of v is negative, then dpx0, basically this is a positive thing. I take positive from one child, and this is negative, and I take the negative maxima of all the childs that has been processed till now. So a negative into a negative is a positive, and a positive, it yields to greater than 0. And I'm writing here plus because I'm considering the powers of 2 and they are added in multiplication. Okay, and if I'm here, then dpx1 stores the maximum negative product, or basically the number of 2's or minus 2's in the negative product of maximum magnitude that starts from node x and ends in some node in the subtree of x, and this is also negative. And here this stores the maximum value of dp u0 of all the nodes u which are the childs of the vertex v which has been processed before x. Okay, so this is how I would solve the problem. It's a good dp on tree problem, and I think that it would require you to know dfs and dp on trees to understand this particular problem or this particular approach. So let's discuss the code on this. So here I have just taken n as 1 e power 5 plus 1, mod as 1 e power 9 plus 7, which is required in the answer. Here is my graph. Okay, and here is my dp table, and denotes the number of vertices. Here is the array, and I am storing the in answer I am storing just the maximum power of 2 in the path which is having the maximum positive product. Okay, and in mx I am storing the maximum value of all the nodes. Okay, so this is my dfs function. As I told you, path 0 stores the maximum of all dpu0 values, where u is a child of v. U is a child of v, the maximum of all dpu0 values where u is a child of v. And path 1 stores the maximum of all dpu1 values where u is a child of v. Okay, and path of 0 is equal to 0 because we are considering the case of a dummy child, and path of 1 is equal to -1 because a dummy child can offer only an empty path which has a magnitude of 1 and the power of 2 in it is 0, and a dummy child cannot offer a path which is having a negative value or a negative product. So it is not possible. That's why we fill it with -1. Okay. Now, as we do it in DFS, if u is equal to the parent vertex, then we just continue. Else we just call the DFS. Okay. Now, if the value of the current vertex is greater than 0, we just check that if the path if basically there exists a path which is having a positive value, suppose that this is the vertex v, and there is a path among all the nodes which has been processed before this node u. Path 0 stores the maximum positive path. This is the maximum positive path, this is the positive value, and you take the positive value of u. So this is positive, and this is positive. All three of them exist, then positive into positive into positive is a positive. Okay. So what is the number of powers of 2? Path of 0 denotes the number of powers of 2 on all of nodes which has been processed before u and are childs of v. And dpu 0 just gives the number of powers of 2 on the path that is having a positive magnitude and maximum magnitude, and starting from u, ending at any node in the subtree of u. And if a of v is equal to, then just add one more power of 2. Okay, so basically I'm only storing the power of 2, and I can obtain a positive product in another fashion. If I have a negative path that I can offer to this negative path of this node u, and this node u can offer a negative path to me. If there are two negative paths that are possible, okay, then I just take this negative value, and I multiply it with this positive value. So this is a positive, these two are negative, so a negative into a negative is a positive, plus a positive is a positive, into a negative is a positive. Now, if a of v is negative, it is -1 or -2, then in order to make it positive, I would consider one child having a positive value and one child having a negative value, because two negatives would cancel out and there would be a positive, so it would be greater than 0. So path 0, if there exists a path which is having a positive value and the current node has an offering of a negative product, then okay, just consider path of 0, which is the positive product path, and dpu1, which is the negative product path, and u yourself is a negative. So negative into negative is a positive, and into positive is a positive. Now if path 1, basically if among all the vertices, among all the childs of vertex v which has been processed before you, path 1 stores the maximum of dpu1. Now if it has to offer something, basically if it is not equal to -1, and the node u also has a path which is having a positive product, then just process it. This is the number of powers of 2 in that particular path, the maximum magnitude negative product path, and this is the number of powers of 2 in the maximum magnitude positive product path, which starts from u, ends at any node in the subtree of u. Now this also adds another power of 2. Okay, and I write this path of 0 is equal to the maximum of path of 0 at dpu 0, and path 1 equal to the maximum of path 1 dpu 1. As I told you that path of 0 will store the maximum of dpu 0 when you are at the vertex u, then you will get to know that okay, I am at the vertex u, and path 0 stores the maximum of dpu 0 of all the vertices which are processed before you and are child of vertex v, and path 1 stores the maximum of dpu 1 of all the vertices that are processed before you and a child of v. Okay, now if a of v is greater than 0, here I am updating the simple values of dpv0 and dpv1. Now if there was some of my child who was offering me a positive path, then I would just combine with that positive path. I am positive, that is positive, so positive into positive is a positive, and so a positive. And if a of v is equal to, there would be an increment in the power of 2, so a of v equal to plus path of 0. Now if there is my child which is offering me a negative path, so I am a positive, it is offering me a negative, positive into a negative is a negative. So this is the maximal value negative path, dpv1 is equal to a of v is equal to, there would be an increment in the power of 2 plus path of 1, which represents the number of powers in the maximum magnitude negative product path among all the childs of vertex v. Okay, and in the same way I do the same thing for a of v is less than 0. If the path of 1 is, if basically if this is negative and the path that one of my childs offer is also negative, or basically the maximum negative product path offered by my child, if it exists, then negative into negative is a positive. A of v is equal -2, it would increase the power of 2, and path of 1 represent the number of powers of 2 on that path. And here is a of v equal -2, this represents the number of, this would increment the power of 2, and path of 0 would basically represent the number of powers of 2 on a path that is of positive magnitude and maximum product among all the childs of node V. Okay, now this is basically the bin power function. You can do this binary, this is called binary exponentiation. And now here t denotes the number of test cases and n denotes the number of nodes. I stored the maxima, initialize the maximum value for all nodes to -3, answer to -1. I just clear the input, I make dpi0 -1, dpi1 -1, I just clear the graph, just process all the edges, I create the graph, and after that I store the maximum of this. Call the DFS function. If answer is not equal to -1, basically there exists a path which is in which there are positive nodes, or basically the nodes with positive values, or basically a path with a positive product. Then I just mx equal to bin power 2 comma answer 2 raised to the power that number of 2's. Answer represents the number of 2's on that particular path. Else if mx is less than 0, then I just add modulo, because I have to return the answer modulo something, and after that I print mx for every test case. So let's submit the solution. You can see that the solution got accepted. If you have any doubt regarding this approach, you can ask in the comment section. And I would like to mention that this was a good problem and you can learn a lot from this problem. You can see that the technique I used here, if you look at that closely, then you will learn a lot. And see the prerequisites. If you want to understand this problem properly, you should know DFS. You should know that how a particular node inherits, basically takes the properties of its child, and how you combine the properties of two childs, as I was telling. Okay, so that is all, and thank you for watching the video.